So, good afternoon, everybody. Thanks for being here in one more session of our Quantum Research Center seminar. And today, I have the pleasure of introducing you to Professor Martin Kliesch from the Heinrich Heine Universität Düsseldorf in Germany. It's really a big pleasure. He's a great scientist and also a good colleague and old friend of mine. Like I said, he's a junior professor at the Heinrich Heine Universität Düsseldorf and head of the quantum technology group there. He's actually there a grantee of the Emineta program by the DFG, and he also has currently other 2 grants by the BMBF program, so he's actually having lots of activity in his group. In the past, he did PhD in the group of Jens Eisert in the Free University of Berlin. That's when I met him. He later went for a postdoc with Professor David Gross in Cologne, also in Germany, and then he had a principal investigator position at the University of Gdańsk in Poland, and that was before he moved to Düsseldorf, right? His interests vary from characterization and verification of quantum complex systems, hybrid quantum classical computing schemes, classical simulation schemes for open quantum systems, and several things connected to computational complexity too. So, and he has of course done several nice contributions to these fields. So it's really a pleasure to have you here, Martin. Thank you for coming. Thank you for being physically here, and please enjoy your talk. Proceed. Thanks.
Yeah, thank you, Leandro. Thank you very much for, first of all, for the kind invitation and also for your nice words. I very much enjoy it here. I didn't know what to expect, and I love it, and it's a very nice time. And I'm also happy to travel again after, I don't know, 1.5 years or so of not traveling. And it's so much more fun than all these Zoom conversations, as you all can imagine. So when I was thinking what to talk about, I asked Leandro, and he said that there will be theory people who are experts on quantum computing and also experimentalists who know other things better, and that I should like have a soft start. And so then I made a talk where I start like with the latest developments, and I basically present my view on them, like starting with the Google experiment basically, and then we will switch gears at some point and talk about variational quantum algorithms. And in the end, I also show you some unpublished results that are being written up right now. So I take you through a grand tour of like a bit of history first, of very recent history, and then in the end, active research. So here's the outline of my talk. I already mentioned that I will first talk about quantum supremacy, and when you work in quantum characterization, you always think about how you can certify things, and we were trying to figure out how one could certify these sampling experiments for showing quantum supremacy. And in the end, we came up with some lower bounds when you have a very strong notion of verification, and when you put this very strong notion on verification on these experiments, we have some no-go results, which I would like to share with you. As I said, then we switch over to variational quantum algorithms, or short VQAs, and here the hope is to have some useful quantum advantage, for instance, in quantum chemistry. But there are, of course, also challenges that need to be overcome, not only experimental ones, but also theoretical ones, which is, first of all, these devices that are hard to train in the worst case, and secondly, the measurement effort that is necessary to make the communication basically between the classical machine and the quantum machine possible. This measurement effort is huge, and we have some ideas on how to reduce this measurement effort a little bit. And I would like to very roughly sketch these ideas, okay? But let's first start with a big picture. So when we talk about quantum technology, we typically mean that one uses state preparation, the coherent manipulations of quantum states, and measurements in the end. And there are all these different fields, like quantum sensing, where you can measure time or gravitation or also other stuff. There's quantum communication, which you all know from the groups here, I suppose. And there are the quantum simulation and quantum computation efforts. And in the quantum computation area, there's a new feature which has not been there before. These systems are so complex that they cannot be simulated by classical computers. And this leads to the hope that they can be used in turn to do computations that cannot be done on classical computers efficiently. Right? So that's the basic hope of quantum computation and also of quantum simulation. And the ultimate goal is to build something like a universal quantum computer, like a fully fledged quantum computer that would support any type of quantum algorithm in a similar fashion as a classical computer supports any type of classical algorithm, right? And yeah, here's a very rough model of what typically is meant by a universal quantum computer. You have some machine, which as a theorist, we like to think of them as being a black box that receives some input of gate sequences and produces, in the end, one does some measurement and gets a classical result. And in the end, we measure each qubit, which results in a number 0 or 1. And we get always these bit strings as measurement results in the simplest model. And yeah, an example for how this machine might work on the inside on a logical level, like not on the experimental level, but on a logical level, is like this, where we feed some initial states into quantum gates and measure them in the end. And right. And then there are one important thing to know is that there are universal gate sets. So there are very simple gate sets of, say, just 4, 1, and 2 qubit unitaries. And arranging these gates in such a circuit, you can approximate any unitary. Okay, not necessarily efficiently at this point, but in principle you can reach the full unitary group and hence all possible evolutions. And then this is why this model of computing is called a universal quantum computer. Universal because you can reach the full unitary group in a way. And this can be used for lots of different things, at least in theory. The all-time all-star is Shor's algorithm, which you all know, I guess, to factor large integer numbers, with which you can break common crypto systems. But there are also more speculative ideas, even like on quantum machine learning and even big data. Yeah, maybe the oldest application is the simulation of quantum systems themselves. So then you could use this to simulate strongly correlated electronic systems, which is relevant in quantum chemistry. These are just 3 examples. The list could be much longer, but I just wanted to give you a few examples. And of course, there are challenges. So these algorithms have not been implemented. What are the challenges? First of all, large quantum systems are noisy. And in order to make these algorithms running, we need huge numbers of qubits. Okay, and typically when we scale up a quantum system, it gets harder to control the noise. And what you usually need is that the noise stays below some threshold. And people have looked into the number of qubits that are needed, including quantum error correction, in order to run Shor's algorithm, and then you need like 10 million of qubits, very roughly, depending on how you count it. You need this number of many qubits in order to outperform what classical computers can do. And yeah, so looking at this noise scaling of real quantum systems, it's unclear whether or not one can ever build a universal quantum computer. So for this reason, a milestone has been formulated, which is to just come up with some problem, might be completely useless, but just have some computational problem, which a classical computer cannot do, but which a quantum computer can do. And this is called quantum supremacy. And this was achieved by Google 2 years ago, as you all know. And let's have a look of what they did on a high level. So they picked a problem which is very natural for quantum experiments. So the task is to measure, to sample from the measurement output distribution. So have some sampling task where the task is exactly to sample from the measurement outcomes, okay? And how the measurement outcomes are generated was done with the superconducting circuit here, which on a logical level, it's a sequence of gates again, which are drawn at random in some fashion. And these quantum gates are applied to some initial state, and in the end they are measured in the standard measurement basis. And now the task, as I said, is to measure to sample from the measurement output distribution. And right, so I like to call this PU. So again, we fix some circuit U, which was drawn at random initially, but then we keep it fixed, and then we want to sample from this distribution, meaning that we sample bit strings. So we have 0-1 combinations, and we need to sample a string of these combinations. So there are 2 to the n many different such strings. Okay, that's important. And when one investigates these distributions in more detail, what one can see is that they are very flat. So they are a bit like this. We have many bit strings on the x-axis, and the probabilities for each bit string are very small. But it's not uniform. There is some structure which makes it hard to sample from these distributions, which in the end makes it intractable on classical computers. But still, all the single probabilities are all very small. And I call these distributions flat, or in technical terms, it means that they have a high min entropy. And for this reason, they are good to show quantum supremacy. But yeah, I will discuss in a moment that therefore there are other challenges on the theoretical side. So of course, building the hardware is an obvious challenge, but verifying that you do the right thing, that you sample from the right distribution, is a theoretical challenge that is also difficult to be solved. And what we were wondering, can such a device, like down here, be verified in a device-independent fashion, where I don't need to look into the device, but say I go to some quantum simulator shop, I get such a complicated device which I don't understand, but I know in principle what kind of unitary, what kind of circuits I have put in the beginning, and then I look at the data in the end. And now I want to decide from the description of the unitary in the data, does the device do the right thing? And more formally, for some target distribution, P, I get samples from Q, and I wish the Q and P are the same, and I get some number of samples, say K, and I want to decide whether or not the distributions are the same, or whether or not they are different up to some error tolerance epsilon. Okay, so here I would be happy, and here I would return the device to the quantum simulator shop, right? And all these statements I made only hold with high probability because I drew the random unitary at some point. But this is a detail, okay? But you do this in the beginning, and then with high probability everything works as I said. Okay, so this would be the ideal situation of certifying such a device. And this does not work efficiently. This is what we proved. The number of samples that you need in order to solve this task scales like this. So you have some standard scaling on the error, but an exponential scaling on the number of qubits n. Okay, and meaning that when you have 50 qubits, then you have something like, okay, then it might still work, but you have something large here that scales badly. And so what can one do? The Google experiment still makes sense, but it's just difficult to certify it or to verify that it does the right thing. And what one needs to do is to use more information to violate this assumption of doing a device independently. So we need to use information on the hardware, on the inner functioning of the device. This is one thing one can do. And then one is maybe also happy with doing a bit less than this very strong notion of certification. So what one should do is somehow verify that it does the right thing to the maximum extent possible, right? And this is also what Google did in the end. When you look into the appendix or into the supplemental material of the Nature paper, and you just count the pages, how much of the theory was focused on characterization of their device on a logical level and on verification. It's actually the majority of this work here. Okay, and for this reason, for related reasons, there's a whole research field focusing on characterizing quantum devices on a logical level. So not something like Rabi oscillations, but you want to get a characterization of the behavior on the logical level, on the level of qubits, okay, and on the level of quantum gates. And this field is like to call it quantum system characterization. That's not something I want to talk about today. I just wanted to point it out because that's my, I would say main research field, and maybe I will talk about it another time. But okay, let's get back on track. So quantum supremacy was done by Google. It's an important milestone, and we saw that it is challenging to verify such quantum supremacy experiments. But then there's also another criticism. It's completely useless otherwise, I would argue. Like you can demonstrate quantum supremacy, you can solve some difficult problem, but the problem that you are solving is otherwise completely useless. And then the next goal, of course, must be to demonstrate some useful form of quantum advantage, right?
Martin, one question before we move to the second part of useful quantum algorithm. So then in the end, so what is the approach that they take for, what is their claim about certification? Like, okay, device independently, you cannot do it. That's what we learn here.
They do cross-entropy benchmarking, they call it.
But can you more or less describe that in few words, like, or if there is any?
Yeah, so
it's at the level of data also, right?
It's on the level of data.
They don't do gate tomography in that experiment, right? Like,
oh, that's true. It's on the level of data, but they need to be able to simulate their device, which cannot be done for the full setting, like when they draw the full circuit at random. They cannot simulate it, but then they simulate it for special instances where they remove some interactions in the some entangling gates,
okay.
and then it becomes easier to simulate.
And they do it brute force with classical computers,
they use a Feynman-Schrödinger simulator. So
some smart classical algorithm, right?
Exactly, to simulate it. And then in a very smart way, they compare the classical data with a simulation outcome, which is called cross-entropy benchmarking, which does not give you a guarantee that you are sampling from the right distribution in total variation distance or in some meaningful distance, but you would be able to detect certain types of errors. Yeah, you can come up with sampling schemes that give you the right measure in cross entropy, but which do something completely different than the Google experiment. So it cannot detect all four types of errors. So in a way, you need to put assumptions on the noise model that they are using in order to say that it does the right thing.
Right.
That's how I understand it. So you make some realistic assumptions on the noise model, plus you have the cross entropy benchmarking outcome, and then you can.
And then you trust. Okay.
Yeah, you can.
Then you hope for the best.
Can hope for the best and trust the device. That's how I read it.
That's great. Okay, thanks.
Yeah, thanks for the good question. Yeah, please interrupt me at any time. I like it when it's more interactive. It's also an advantage of being here in person. Yes, so when there are no more questions, I move to the next topic, which is finding possibilities to getting some useful forms of quantum advantages. But before we do that, let's have a look at the situation again. Okay, we have all these impressive devices, quantum devices here, and they are all limited in by the qubit numbers. Like we saw in the Google experiment, they can have like 53 qubits or so, and they are also very limited by noise, of course. And we cannot do something like a quantum error correction because this has a large overhead. If we could do it, we could reduce the noise effectively, but that's not possible at the moment, and also not in the next couple of years at least. Okay. And so the question is, what can we do in the meantime? And one big candidate to achieve a useful form of quantum advantage are so-called variational quantum algorithms. The idea there is to have a classical computer and a quantum computer, some noisy quantum device, working together in order to solve some useful problem from quantum chemistry, for instance. And how this is always done for these types of algorithms is to encode some relevant problem from quantum chemistry or optimization or so into the ground state of some qubit Hamiltonian. Okay, and I would like to explain in more detail how this works. So in the end, we want to minimize some expectation value. Okay, and the expectation value corresponds to having a noisy quantum circuit where we initialize the device in some reference state, typically this all zero state, and then we apply a gate sequence to it. Can be anything that the device can implement. Okay, and it's good if you can reach when it's more complex. But this the game on how to implement these gates depends on the device that you would have. But you can take some model and come up with a collection of circuits that you can implement, and in the end you again do a measurement. What is different to the approach that I've described before to the universal quantum computer is that here you consider these unitaries to be parameterized by some parameter. Like any unitary is generated by some Hamiltonian when you implement it like that. So you can write it as e to the minus iht. And then you can choose the time, how long you basically apply this Hamiltonian, right? And this gives you effectively this parameter, which you can choose on external knobs of your quantum device. Okay, so the game is like this. We put in a set of parameters. In the end, we measure, and then by some processing, we reconstruct some expectation value. And I like to call the observable of which we reconstruct the expectation value, I call it the cost Hamiltonian, because in a way in the end we want to minimize something like here, and then we effectively minimize the expectation value of the cost Hamiltonian. And then the hope is in the end to find the ground state of the problem we started with. So we wish to find the ground state of the cost Hamiltonian, and now we can play with the parameters. And how this is done is to use some classical optimization routines. So one could, for instance, apply some form of gradient descent and then go downhill and hope for the best that we achieve the ground state in the end. Okay, so this is how variational quantum algorithms work, like on a relatively high level. And there are very popular variants. One are so-called variational quantum eigensolvers, which are used to solve electronic structure problems, so problems from quantum chemistry and from material science, where you typically have some fermionic systems of which you wish to find the ground state energy, also excited states. And you map this to qubits into such a circuit here, and then you can use this to actually do this minimization. And this has been demonstrated also on small systems. Just to demonstrate it, these small systems are all classically simulable, or classical algorithms do much better, but in principle this works. Okay, but it's unclear how it scales when you go to large qubit numbers or large problem instances. This is one variant. Another variant are discrete optimization problems, where one has some combinatorial problems that one can map to discrete optimization problems. And there is one. The most popular one are these quantum approximate optimization problems, or short QAOAs, and typically very often they are investigated on what's called the max cut problem. I'll explain more in a moment what that is, but the idea is to find the maximum cut through a graph. Okay, and this can be mapped to the ground state of a Hamiltonian and can also be solved in such a fashion here. Okay, on a small scale, this has been implemented for quantum chemical systems, but it's unclear how this scales. So again, there are some challenges. So the first one is the measurement effort that I have mentioned in the beginning. So when you run this iteration loop, you have the post-processing and the measurement step here. And when you want to feed this back, you need to do a lot of measurements, also because the measurements are probabilistic. So this gives some bottleneck of the whole approach. And the another challenge is to run the classical optimization. There are two common problems that can occur in classical optimization. When you minimize some function, like here, then yeah, you could get stuck on a plateau, and the optimization landscape could get very flat, and you don't know in which direction to go in order to minimize your function. And the other problem, of course, is that you could get stuck in local minima. And the first problem, the plateau problem, has been investigated under the name barren plateaus. This is the original paper here, but by now there are, I don't know, at least 10 papers or so. And they have thoroughly investigated these plateau behavior and how one can play with the circuit architecture here in order to, yeah, avoid these plateaus to some extent. Okay, and what people have not looked at are local minima, surprisingly, because this somehow seems much more obvious to me, but this has not been thoroughly investigated, and that's what we did. And what we show is that it can be very hard to escape these local minima. So some local minima might be easy to escape, like when the plot here is a bit misleading. What you have is an analog in high dimensions, right? And then when you have a local minima, you could try to run in one coordinate direction or so, and maybe get away from your local minimum and find some smaller value of your cost function. Okay, but this does not happen necessarily for these type of algorithms. And what we constructed is essentially an example of a cost function in the setting where the local minima are difficult to escape from. And we show that it's actually hard to find the global minimum. So this is basically how this is connected to local minima. And before I say more about it, maybe it's good to remind you of the jargon that is used when you talk about hardness, right? In the easiest case, one talks about decision problems, which is a technical detail here. These are problems with a yes or no answer. For instance, does some large integer number have a non-trivial factor larger than k or so? Yeah, then you have factoring rephrased as a decision problem. And then there are two important classical complexity classes. The one is, there's P, which are all decision problems that can be solved in a time that scales polynomially with the input size. So with the number of digits in case of multiplication of integers, let's say. And we call algorithms that solve problems in polynomial time, we also call them efficient. So that's some special jargon that we use. Okay, so it means that something scales polynomially. Is also always when I say efficient, it always means that something scales polynomially. Okay, and then there is a much larger complexity class. Well, I say it's much larger, which is called NP, and these are all problems that can be verified in polynomial time. So, for instance, when you want to factor integers, this cannot be done in polynomial time. But if I give you two integers and ask you, do they multiply together to the original integer, then you can check, right? You can check if a factorization is correct. And actually, these types of problems are in this class here, okay? And there's a conjecture that these classes are not equal. So NP is much larger than P. That's what we generally believe, okay? So that's a very strong belief, like to the extent that we base the security of our banking system on that belief, okay? So we can assume this is true. Okay, let's get back to the hardness of our optimization problem. So we wanted to minimize this expectation value here by playing with these phi parameters with the classical algorithm. So this was the goal, right? And I want to formalize this algorithm, this problem a bit better, because it's a bit tricky, because we want to capture the difficulty of the classical part without taking into account that also the quantum part might be difficult. So what I want to assume is that somehow the quantum part, the quantum computer, is given as a very perfect device, and I just want to understand how difficult is it to solve this classical part. Yeah. So I want to separate these two computation tasks, and how this is done is typically in terms of so-called oracles in computer science. And in computer science, you always phrase a problem in terms of some input that you have, and some tasks that you need to fulfill. And here we have a third point, which is the oracle. So I'll walk you through it. As the input, we are given the set of generators which generate the unitaries in this form here. Okay, and the generators are given, and also I need to know what I want to do, what the cost function is. Okay, so I assume this is also given in terms of some observable HC. And there's some fine print. I cannot take this as huge matrices in an exponentially large Hilbert space, but I need to have some efficient description of it, so I can represent it in the Pauli basis and have just a few summons in the expansion in the Pauli basis or so. So any reasonable physical Hamiltonian can be compressed in some form. And then I take this as input. And now in the problem, I assume that when I try to find the parameters that minimize the objective function here, I assume that I have access to the oracle. So I assume that I have some machine or some information source that provides me this expectation value for free. So I put in the phi, and the oracle gives me back the expectation value, which ideally the quantum computer would do. Of course it couldn't, but it's an idealization. Okay, and even with this idealization, this problem is NP hard to solve. So this means yes?
So this means also that you're assuming that you have like a very good estimate of your expectation value without statistical errors, for instance, right?
Yeah.
Like, right. So as to capture the complexity of just the optimization of the phi.
Yes. Thanks.
Correct? Okay.
Yeah.
Thank you.
Exactly. Yeah. So I have some like this is a real number in general, and I get this real number up to some cutoff of the large digits, which I don't need. But I get the exact expectation value exactly. If I would do this even if with a perfect quantum computer, I would need to do measurements, and so I have some statistical errors just from the quantum measurements, which would give me some statistical error on top of this expectation value. But as an idealization, I can assume that I don't have any noise, but I get the perfect expectation value. And one could also prove this with statistical errors, the hardness, but it's much more technical and does not carry any more insight. That's right. Now minimizing this expectation value over the parameters of the quantum circuit is a hard problem. Or in other words, there is no efficient algorithm that runs in polynomial time in the input size that can do the minimization. Okay, this is our first small result, and then we have a sequence of other results which I will only sketch. Okay, but I think it's insightful to have a sketch on how one can prove this more simple result. Okay, so how one can prove hardness is always that you need some other problem that is hard. When you want to prove a problem A to be hard, then it's good to have a problem B that you already know to be hard, and then you derive the hardness from that. So we need such a problem, and we take max cut because this is well investigated in the context of variational quantum algorithms. And now we show if the optimization algorithm here, the classical optimization, can be solved efficiently in polynomial time, then we could also use that to somehow solve the max cut problem. Since we don't know, since we know that solving max cut is hard, also the optimization problem must be hard. Okay, this is the line of argument one always follows when one shows something to be hard. And this is exactly what we do here. So here I explain a bit more what max cut is. It's an interesting problem in its own right, and it has been used a lot in this in the quantum community right now because it's an interesting discrete optimization problem in the end. And it's about graphs. So we take some graph. It's unweighted and has no self connections. So it's a graph like this, and we label the vertices by numbers. Okay, I call them 1 to d, so it has d many vertices. And then I also need to say what the edges are, and I do this by writing down the adjacency matrix. Okay, so I take a matrix, a large matrix, of which the columns and rows are labeled by vertices, and then the entries are 1 when the vertices are connected and 0 otherwise. Okay, that's called the adjacency matrix. And it's some matrix that has nice properties. And now the max-cut problem is a problem on such a graph. So as input, we take such an adjacency matrix, and in our back of our minds, we have such a graph. And now we are tasked to make two groups of the vertices, say to color them in black and white, okay, so that the edges between the two colors is maximized. Okay, and one can mathematically phrase this like this. So a bipartition can be given just by saying what the say black vertices are. This is in the set S, and then here the sum, we let it run over all edges basically. So all pairs of vertices that are in S and not in S, and then we count the ones that we have here basically. And this gives us the number of cuts that are given by S, and then we want to maximize it. And that's a problem that is very interesting. So it has very nice properties which are well investigated. First of all, there's an so-called, one can define an approximation ratio. So when you have some solution that approximately tries to maximize the number of cuts here, and you have some assignment, some S, so some assignment of colors to your graph, then you can count how many edges you have that are returned, say, by some algorithm, and you can divide it by the optimal solution. So that's a number that is between 1 and 0, and it's 1 when the algorithm finds the perfect solution, and smaller otherwise, okay? And now what has been investigated is how well polynomial time algorithms, so algorithms that are efficient for classical computers, how well they can find such such assignments of cuts, okay? And they can achieve an approximation ratio up to almost 90%. So your classical computer can do this efficiently up to 90%, but then going further is in general NP hard. Of course, there might be graphs where this is easy, like when you take the graph with no edges or so, it's completely trivial, but for arbitrary graphs, it can be more difficult, so that you get this approximation ratio, which is the maximum for classical algorithms, and the upper and lower bounds, and they essentially coincide. There's again some fine print, so the complexity theorists, they like conjectures, okay? So when they cannot prove something, they just, but they believe very strongly that it is true, they call it a conjecture and work with it. And here this uses the unique gains conjecture, but when you don't like it, you get some other value, okay? But the interesting thing is that there is an approximation ratio. So even approximating the problem is already hard, not even finding the optimum solution. So now we have our discrete optimization problem.
How do they know what the optimal solution is? I mean, actually your problem is solved.
So you're wondering how can you prove the hardness without knowing the optimal solution? Yeah, this is again such a reduction argument that we are also doing here again. So how you do this is you look for some other problem where you already know that it is hard, and then you show that this other problem where you know it is hard, that you could solve this efficiently if you could beat this approximation ratio.
Okay.
Yeah.
But
So you don't need to know the optimal solution to show that this approximation ratio is the maximum you can achieve, if that makes sense. Yeah, good question. You have always this chain of reduction arguments in complexity theory. You always need a mother problem that is hard. Right, so here we have a discrete optimization problem with some discrete input in this matrix here, and we wanted to map it to the variational quantum algorithms, right, which was some continuous optimization problem. And in order to go a bit closer to the variational quantum algorithms, we take a slight reformulation of this problem. We also turn it into a continuous optimization problem. And how we do this is we take again a problem with the same input, but then we try to find the maximum, or okay, here I changed the maximum to a minimum of some continuous function that I explain here. Okay, so I walk you through it. first I want to just to point out that I changed the maximum to a minimum because in the end we want to minimize energies, expectation values of Hamiltonians. And in the max cut problem you want to maximize something, and at some point you need to do the switch, and I like to do it here. But yeah. And structurally this is the same problem, except that the optimization of the function is different. So let's have a look at the function. We start with this function and rewrite it like this. So that's I would call it an Ising type Hamiltonian encoding of this problem here. And the idea is that we have now we assign -1 and 1 to the vertices here. Okay, so say the black vertices are 1 and the whites are -1. And when the I would be the assignment of the ith vertex. Okay, and now we have here an Ising type term. So when the I and the j are the same, you get a value of 1, and when they have opposite sign, we get a -1. So always when they have opposite sign, we get a negative contribution here, and when you maximize this negative contribution, in the end you get the maximum cut. Okay, and we rescale this in some convenient standard way. And now it's very simple to turn this into a continuous optimization problem. We just replace the discrete variables by cosine functions, and we optimize over the angles in the cosine functions. And what might happen there is that you introduce some new minima, right? We make the optimization space larger, so some new minima might pop up. But this does not happen, which is something we can prove. Hence, this problem is also hard in the same sense. So that's a difficult problem, and that's the problem we are going to derive the hardness from in a moment for the max cut problem. And one important thing to note is that also the approximation ratio is inherited. Okay. Yeah, that's a proof sketch. Maybe the fine print doesn't matter, but now we can choose a Hamiltonian given some adjacency matrix and choose some generators, and we play with everything so that in the end, that's the important thing here, that the expectation value of our cost function Hamiltonian here is the same as this continuous max cut function that we defined down here. So when we can minimize the Hamiltonian expectation value, we can also minimize this continuous max cut function. Okay, so in a way the problems are equivalent. So when you can solve the continuous problem, you can also solve the discrete problem. You cannot do this, hence the optimization here is an NP-hard problem. Okay, so this is, yeah?
Martin, so
thanks.
The Hamiltonian is fixed here, is the equivalent to the max, is the max cut problem Hamiltonian, and then what you do is to play with the gates essentially, right, by choosing those Hamiltonians HI.
Yes.
And then that's how you make the, so the gradients would be related to these phi i's, right, like the gradients that you would like to estimate.
Yeah, here we are not even talking about gradients. So how you do the optimization is up to you. I'm just saying if you can do the optimization, then you can also solve the max cut problem.
Right, I see.
Yeah.
Okay.
Yeah.
So it's even more general, right? Like
yeah.
In whatever means you take to do this optimization, you reduce it to an NP-complete problem, right? Okay.
Exactly.
I see.
Yeah.
Okay.
It's independent of the algorithm for the optimization that he's using.
Okay.
Exactly.
Fantastic. Very interesting. Very interesting. Yeah.
I didn't see the second Hamiltonian. Why do you choose this, or is it? I mean, what is the total Hamiltonian? Then is it HC plus HI, or?
HC is the Hamiltonian we want to find the ground state of.
Okay.
Is this your question?
And this HI?
The HIs are the generators to generate the variational quantum circuit.
The gates.
That's maybe, yeah, maybe.
Thanks.
Let's go back. Yeah. So when we had this problem, this problem of doing the minimization, where we said that the input is the cost function Hamiltonian plus a description of how we are allowed to build the circuit, and this description was given in terms of these generators here. They generate the unitaries, and then we pick them. So here we pick the input, which is the adjacency matrix and the generators, and then the output we want to have is the expectation value. Right.
I do have another question. So I agree that any classical optimization algorithm you can do will have to be NP hard if not to solve the image hat problem. But is this a statement about training BQAs, or is it a statement about training BQAs for solving the image hat problem?
It's a statement about training VQAs. So, well, you call a problem hard when you find a hard instance. So one hard example of the problem must be hard. Of course, there's always you can always find easy VQAs. So when the Hamiltonian is something totally trivial, then you can solve that. Say it's not interacting or something. But here the point is that you can run into accidents when you get, for instance, when you take the Max-Cut Hamiltonian. Or potentially also some other stuff that we don't know, but in general this problem is hard. You're driving me towards the conclusion of this topic here.
Because of course, if you're trying to solve a hard problem, it will be hard to optimize the parameters to solve it as well.
Yeah, right. So what this means is that there cannot be one algorithm that can solve all problems of this type, right?
Sure.
This excludes some such an algorithm from existing. Yeah, this is. I would like to come back to this in a moment.
So I would like to connect with another question, because I think I start to understand deeper like what you saw. Yeah, it's very interesting, but I think that there is something to what he's saying that is true, that actually the nicest thing would be to show that you get like finding the angles solves so if you could show the same thing but for a Hamiltonian whose ground state is not the solution to an NP complete problem, then that would be even stronger, right?
Right.
Because
So
it's true that the Hamiltonian itself here is already complex.
Yeah, this relates to the second point here.
All right, sorry.
Yeah, you're thinking ahead there. Very good.
Sorry.
So this was the proof sketch. But I'm a bit too slow.
No, it's
but
being slow is great.
Yeah.
These technical issues is fantastic.
But yeah, so this is basically something very simple that is like with the knowledge in the field. This was sort of, I would say it has been folk knowledge without anybody having it written down precisely. But then we went some steps beyond it. We were wondering what happens what happens with approximate optimization. So often it's sufficient to solve optimization problems approximately, and we already have this approximation ratio. So this can be used to also show that approximate optimization is hard. Then we're wondering exactly the same thing. Can one get rid of the oracle, or in other words, can one find a problem where finding the ground state is not hard, but where the classical optimization is hard, which relates to your question. Yeah, and then we also were thinking about other architectures, like when you have something like QAOAs or so, when you have more constraints on the circuit architecture, if you also get hardness in this case. And yeah, the answer to all these questions is basically yes. So I quickly walk you through the approximate optimization. So we want to find the minimum eigenvalue of our cost Hamiltonian, the ground state energy, and we have something that is returned by the algorithm. Some value that is higher, potentially higher than the minimum here. And now this error that we have in the end has two contributions. So the first contribution is that when we take the minimum over all possible circuit parameters here, okay, I denote this by this expectation value with the min, then this might still not be the ground state energy if the circuit would be unable to reproduce the ground state. Then you get some higher energy. And there's nothing the classical optimization can do about it, right? And then there is another accident or another error that can occur, is that the algorithm can return some value that is not the global minimum. And this is the thing we want to look at, okay? And you can look at, here's a diagram for that. And what we can show is that So trying to make this small is also a hard problem. Or in other words, there is no polynomial time algorithm, so no algorithm that you can run on your computer in a reasonable time that gets a guarantee on the optimization error of this type. So here we again have this optimization error, the error of the algorithm, and then we normalize it by basically the width of the spectrum of the Hamiltonian. Okay, so that this is some number on the left-hand side between 0 and 1. And now for any threshold that you can choose, and any number that you can pick that is smaller than 1, this is a hard problem. So this is as dramatic as it can be. Okay, like any approximation error that is non-trivial results in a hard problem. Yes? Oh, the microphone. Or you can also ask and I repeat it.
Yeah, don't you have to know the spectrum of the Hamiltonian to talk about the gap of the Hamiltonian?
Yeah, that's why I took such a formulation that you cannot find a guarantee of this type. But the issue is not finding these values here. I could also put the operator norm here or some bound on the operator norm, but then it would be more difficult to make the statement precise. But you don't need to know it. It's just okay. Hardness results always should tell you that algorithms of certain types that are efficient do not exist. That's how you should understand it. And what you cannot do is to have a guarantee of this type, if that makes sense. And you don't necessarily need to know what these values are in order to have the guarantee, if that makes sense. Okay. Okay, the proof sketch is actually very, very simple. That's why I want to show it, even though I'm sort of out of time. So we had the approximation ratio of the max cut problem earlier, these 90%, and this translates into the optimization error directly in this kind. But then we can boost it by taking several tensor copies of the system. Okay, so this is not completely obvious, but when you write it down, it's not so difficult to see. Okay, and then there were other questions. Like here, we encoded the hard problem into the ground state of this cost Hamiltonian. And yeah, then when we make the cost Hamiltonian efficiently simulable on classical computers, then we don't need the oracle. And then finding the ground set is also not hard when it's, by assumption, efficiently simulable. And two ways to do this is to go to small Hilbert space dimensions. So we take, one way to say this is we take logarithmically many qubits. Then we can use exact diagonalization to find the ground state. So finding the ground state is not a difficult problem. But what we can show is that doing the classical optimization is still a difficult problem. And this relates back to the errors. What happens in this case is that the ansatz class here is not able to capture the ground state. And then you can also run into local minima problems. This is what we show. And then we play around with it and also show that you can even go to one layer in VQAs. And a related problem is when you have an expectation value that evolve in time, and you want to minimize this expectation value, then it's also an NP-hard problem, also for small Hilbert space dimensions. And one other way to make quantum systems efficiently simulable is to assume that it's given by free fermions. Then you still have an exponentially large Hilbert space, but you can calculate the ground state energy efficiently on classical computers. And then this also becomes a hard problem. Okay, and I don't show you the fine print here, but just wanted to outline the results. So what we have shown is that.
Can I make a question? Yeah.
Yes, sure.
I'm not sure if the question makes sense, but what would happen now if instead of having a classical problem, so a diagonal Hamiltonian, I have a Hamiltonian with off-diagonal terms? So I know that finding the ground state of a quantum Hamiltonian can be QMA, hard.
Yeah.
The problem. So can I have any results on that with this?
In small Hilbert space dimensions.
Okay.
And
because you are proving that training BQAs is hard because you are trying to solve an NP hard problem.
Yes.
What would happen if instead of having an NP hard, I have a QMA hard problem?
Yeah, I see. I get your point. Yeah, we are working on that. Yeah, we think that we can show that with very simple measurements. So here we measure the full system, but in our new work, we only measure 1 qubit. And we think that this problem then, in a way measuring only one qubit makes it a bit easier. And we think that these problems are actually QCMA hard. So it's like QMA, but where the proof is classical. With a classical proof. It's like QMA, but with a classical proof. And yeah, it cannot be QMA hard because you have a classical proof always. You can, these parameters are a classical description of your solution. But it can be QCMA hard, and we think that it is the case, and we think we have a proof. Yeah, yeah. This is what would be the outlook in a moment. So just to outline the main results that we have seen so far on VQAs is that training VQAs is NP hard in lots of different settings. Like I fully showed you the easiest setting, but then one can extend that. And it even holds for constant relative approximation errors. Like it's, in a way, it's as bad as it can be, at least in this worst case complexity language. And the reason is that you get, yeah, we call it persistent local minima in the optimization landscape, which are difficult to get away from. And so now the important thing is what should this tell us? Should we stop researching in VQAs? The answer is, of course, no. And there are related situations. Like, for instance, the hard-free-fog method also is, in general, gives you some optimization problems that are NP hard, but still it's a very useful method. The same holds for DMG, or same for artificial neural networks. Like training a single rectified linear unit is already an NP hard problem. Nevertheless, these rectified linear units are very useful in all sorts of fields involving neural networks, right? And yeah, so what does this tell us? So first of all, it's a justification of heuristics. So I said this before, you cannot have a single algorithm that generally solves this classic optimization problem. But you need to come up with problem-tailored solutions in a way. So I see this as good news because this means that we have lots of work to do. And so they're interesting problems. And yeah, a practical thing which should tell us is that we should maybe pay more attention to local minima when thinking about developing classic optimization routines. Okay. Yeah, I had more prepared, but I think I'm out of time, and this would be a good cut. I can tell you more about it later if you like, but I would like to skip to the end. Oops, I don't find the end. Here's the end. Okay. Yeah, the work was done by Lennart Bittel on the second work on the hardness results, and the previous work was with these three guys. And yeah, I would also thank my full group. We joined recently together, and it's nice to work with them. And I would like to thank you very much for your attention and also for your great questions.
Thank you very much, Martin, for such an interesting talk, and congratulations for the nice results. And also thank you for doing it so pedagogically and didactically, your explanations. I think that this was a very useful presentation for many people here. We have some minutes for questions, and I would like, oh no, do we have questions by some junior student? Any, who? Sergey, okay.
So I have a question more related to the first part of the talk, so the benchmarking and characterization of quantum circuits. So let's say I put together a bunch of qubits.
Yeah.
And I want to call that a quantum computer. What would, in your opinion, be some sort of... so what should I do to convince you that I have a quantum computer in my hands?
Are you thinking in the quantum supremacy mindset or in the useful quantum computation mindset?
Well, in like what kind of benchmarks or what kind of standards should I pass to let's say convince you that I have some sort of quantum computing device and not some like a bunch of qubits together that sort of behave?
Yeah, that's a good question, also a difficult one.
Mm-hmm.
And one probably not with one answer. It depends on what you're interested in, right? So, of course, there's something like these quantum supremacy demonstrations, but then we are also sort of unhappy about that because we cannot achieve this device-independent verification. So if you have an adversarial scheme where we are back to this picture. So we have some quantum simulator shop, and we cannot trust the guy who sells the stuff, right? How can we make sure that we actually get a quantum simulator? And we are maybe not allowed to open it. Maybe we don't even have the device physically, but just as cloud service or so. This would a scenario what could imagine that, I don't know, Google develops a quantum computing cloud service, and how can we now check if they actually do quantum computing, or maybe they are just using their super powerful supercomputers or classical computers, right? I think that's I think there is not a you're asking for like a computational based build test, but in an adversarial scenario, I guess. And I think this is a bit unclear on how to do this, I would say. Like if you can do Shor factoring, if you can, then it's obvious. Then I would be convinced that Google has a quantum computer if they can factor huge integers. But the intermediate regime, I think it's difficult.
I think, okay, as soon as the machine is universal enough, there are like these schemes of blind computation and verification, like interacting schemes of like message passing. But your quantum computer must already like be a fault-tolerant quantum computer running big circuits in order to do this.
Yeah, right. There's also blind quantum computation, and as soon as you are universal, when you have a fully fledged universal quantum computer, then the answer is clear. But for the NISQ regime, for this noisy intermediate scale regime, it's complicated. Yeah, it like when you can come up with a good test, would give you a very good publication, I think.
Do we have any other question by some student? I have one question. I'd like to understand better what you show. So what is it that you show in that when you're showing this constant fraction of the energy difference between the maximal and the minimum eigenvalue? I don't want to understand the proof. I just want to understand the statement there. Here.
Yeah.
So what is it exactly that you're saying here? So lambda min is the overall minimum energy.
So lambda min is down here
of a hard Hamiltonian, right? In this case. Okay.
And then there's the global optimum over all possible parameters, which is hard to find.
For your variational ansatz, right?
For your variational landscape, but we just define it to be the global minimum. It's hard to find, but we can use it for the statement. And then there's a value that is returned by our algorithm, right? And now, what we want to say in the hardness result is that making this gap here, making this small, is hard.
But to any constant fraction of the bandwidth of your Hamiltonian.
And so give me a moment.
Sorry.
So we want to say that making this distance here small is hard, and we want to say that it's already hard to do this approximately. So then we need to normalize it somehow in order to make it, I don't know, the Hamiltonian, you can rescale it and shift it and stuff, and we want to be invariant under these rescaling and shifts. That's why we have this normalization here. But maybe forget about the normalization for a moment. We want to say achieving going down here is hard, and when we have the maximum value up here, the problem is already hard to just go down a little bit by delta. By going down by a delta fraction is already hard.
So this sounds very strong to me.
Yes.
But so it's really beautiful. But I still want to but does this imply, because this is about making the gap between your algorithm minimum and your variational ansatz minimum, but does it mean also that does it also imply that finding any approximate solution of the original Hamiltonian up to this same fraction of the bandwidth is already hard?
You mean the energy minimization problem without the VQA? No.
Right.
The same holds for for logarithmically many qubits.
Pardon me?
The same holds for logarithmically many qubits. When you just have a logarithmically number of qubits, the polynomial Hilbert space dimension, then this problem here is also hard. But finding the ground state, the perfect ground state, is not hard.
I see. Okay.
Yeah.
Okay, right.
So it's an artifact in a
It's
in
an
a way
artifact of the.
of the VQA setup,
All right.
basically.
Okay,
Yeah.
now I get it. Okay, thanks.
But actually, if I have understood this correctly, the lambda max and lambda min are the actual ground state and highest excited state. And this difference is rather large. And this, in particular, it's larger than every distance you can have above. So I don't understand how you... I mean, if you put there, for example, delta equals 0.9, then I would guess that on average you will always be below this.
I think that's what I was asking.
Yeah.
No.
I mean, lambda max is the maximum eigenvalue of the Hamiltonian. Lambda min is the absolute minimum, and this is at least larger than everything you can think upon below, above. Actually.
But that's what he meant.
Yeah.
So, sorry, I think I can translate. So I think that's what I asked him. The same thing. Like, he's not saying that there is no method for finding any approximate solution to your ground state with delta proportional to the maximum eigenvalue, for instance. He's saying that making the gap between the algorithm minimum and the model minimum, making that gap that small is hard. So it's an artifact of this variational optimization, right? He's not saying that for any other. He's not saying that there is no other way to approximate the ground state that cannot be done efficiently, right? If I got you correctly, right? Anyway, I think that okay, we can.
So
Martin will stay around here for a couple more days. We can.
Yes.
I'm happy to have more discussions. Yeah.
Definitely, yeah. But maybe let me comment. Like,
Please.
what the statement says, that is, I can construct Hamiltonians where when you choose these parameters and you try to minimize them, you're always in the very high to the maximum energy. Like, one can construct Hamiltonians and together with with such a VQA layout that however you choose your parameters, that you are very high in the energy landscape, and it's difficult to find the minimum over the parameters. Like, even going a little bit in the direction of the ground state energy is already hard, like a delta fraction. But these are, of course, they are not, in a way, they are not very natural Hamiltonians. They come first from from the max cut problem, some encoding of the adjacency matrix, and then we take many tensor copies of that. So that this gives something weird. You also lose locality to some extent.